Introduce Alice Gast, who's actually going to moderate the evening for us. Professor Gast, who joined MIT in 2001 as the Vice President for Research and Associate Provost, holds the position of the Robert Haslam Professor of Chemical Engineering. Previously, Professor Gast was the Associate Chair of the Department of Chemical Engineering at Stanford University. Professor Gast, who earned her PhD from Princeton, is an expert on complex fluids and colloids. Did I get it right?
They're nanoparticles now.
Nanoparticles, oh, so it's easier. Her research explores the frontiers of the chemical physics of nanoparticles and polymer solutions, polymer absorption, and the most recently proteins using experimental scattering methods and statistical mechanics. Professor Gast graduated from University of Southern California. Is that the #1 football team from USC?
It was at the time, yeah.
Still is, I believe.
They went through a bad stretch there.
Where she received a BSc in chemical engineering. She went on to earn MA and PhD from Princeton. Professor Gast is a member of the American Association for the Advancement of Science, the American Chemical Society, the American Institute of Chemical Engineers, and the American Physical Society. Thanks very much.
Thank you. I'll have to make sure I paid all my dues at those places, so we're going to talk about it. I'd like to welcome you, and I'd like to thank PricewaterhouseCoopers for their support of this event. This is, for me, one of the most enjoyable evenings of the year because it gives us a chance to showcase MIT faculty and MIT research, and so I have a great time doing this and really enjoy the talks. I've had the pleasure of doing this, and this is the third such evening, and so I think by now, by the end of the evening, we'll have introduced 10 such faculty. So we have another 965 or so to go, so we'll have plenty of these evenings ahead of us. Just to tell you a little bit about MIT, where I'm the VP for research, and we look at a lot of metrics for research, and it's good to understand a little bit about what happens here. Somehow in this limited space we have in Cambridge, we have about 1,000 faculty, as I mentioned, over 6,000 graduate students, about 800 postdoctoral associates, and 4,000 undergraduates. And all of those people contribute to and participate in our educational and research programs. We do have a very strong undergraduate research program as well. We have a lot of metrics for research. We always talk about on campus having more than $500 million worth of research, which when you do the math, that's about $500,000 per faculty member on average. And so it's a quite productive, hyperactive, very energetic faculty. I found out recently that it's another metric that might be more interesting is that there are over 3,000 separate grants and contracts going on here. So we also have quite a bit of diversity. It's not just a couple of big chunks of change funding that research. And these faculty in their spare time manage to make more than 500 invention disclosures each year. And so we have that tendency that people are always asking about how do you get so much innovation out of research, and how does MIT produce so many inventions? And I think it's just part of the culture here. We have a faculty that are, as the three we'll be introducing tonight, are extremely top-level scholars in their respective fields, but they also have an eye to what good their work is for society, and they're always thinking about solving hard problems out there in the real world, and that just naturally results in many innovations and invention disclosures and other such activities. So again, it's a great pleasure to start off this very enjoyable event by introducing one of the newest members of our community, Professor Sangeeta Bhatia, who joined the Division of Health Sciences and Technology and the Electrical Engineering and Computer Science Department this year. Prior to this, she spent 6 years in the bioengineering department at UC San Diego. She's highly recognized for her leading research in tissue engineering and has received dozens of awards, among them the David and Lucille Packard Award for the nation's most promising young professors in science and engineering. She was one of MIT Technology Review's 100 Young Innovators, and she was named one of San Diego's 50 People to Watch in 2004. And unfortunately for San Diego, they watched her leave. Her primary research focus is on tissue repair and regeneration using micro and nanotechnology tools. I had the pleasure of reading one of her papers recently on a liver-derived biomatrix, using actual cells to create a matrix to grow cells and feed them and have them effective. She co-authored the first undergraduate textbook on tissue engineering and holds quite a few patents for both clinical and biotechnological applications of engineering principles. As if that wasn't enough to keep her busy, she also co-founded a group called Keys to Empowering Youth, KEYS, which is an outreach program designed to inspire and empower young women to enter the historically male-dominated fields of science and engineering. So I'm very much looking forward to her talk. She'll be telling us about some of these recent in vitro models of liver tissue and its implications for drug development. And I think it's entitled Liver Tissue Engineering at the Microscale. Welcome, Sangeeta.
I'm going to move you. Is that okay? Yeah. Thanks very much for the introduction and the warm welcome. Let's see how this goes. Try that again. Oh, great. Okay, this is it's only on my screen, but that's fine. Okay. So thank you very much for inviting me here today. I'm going to try one thing. I'm sorry. I can't see it on my screen. I guess it's either or. Yeah, that's how it usually works. All right, great. So I'm happy to be here to share with you our work in this area today. I thought I would start with a little bit of a background. I'm not sure the level of the audience, so I apologize if many of you have seen this pipeline slide before. But this is the problem as we see it, and the technology I'll show you, I think, helps to address at least part of this problem. This is the drug development pipeline. So it costs $800 million to develop a drug or more. And as you can see through this pipeline, there's various stages through the process. Is there a laser pointer, actually? Thank you. You're our stand-in AV guy and speaker, multi-talented. Okay, so Tim pointed out earlier that I can't point to both screens without insulting somebody, so I'm pointing to the right screen for the purposes of this talk. So this is the pipeline, and as you'll see, there's preclinical stages of the pipeline where you discover new compounds and you test them in vitro, and then there's the clinical stages where they go through phase 1, 2, 3 of clinical trials, and then things get registered at the FDA and approved and marketed. So it's important to notice over here on the right-hand side is that much of the expense in the pipeline occurs once drugs enter human trials, okay? And in fact, when drugs go through this whole process, many times, 50 to 60% of the drugs that proceed all the way through the preclinical process, so they're identified as what we call lead candidates, actually go on to fail in human testing. So this preclinical process is actually very inefficient both for safety and efficacy. Of the drugs that get all the way through the pipeline, all the way to humans, up to 1/3 of them fail, specifically due to toxicity in the liver, so drug-induced liver disease. So why is that? One of the main reasons is that the liver is the center of most drug metabolism, and as a result, it's often injured. So the goal for our work and many others in this field is to try and improve the predictions earlier in the pipeline before it gets very expensive so that drug companies can make better choices. And in particular, what we've sought to do and what others have sought to do is come up with better tissue models of human liver specifically. So I'm not going to go through all the things that pharmaceutical companies are trying to attack this problem in detail, except for to say that you can take liver cells out of the liver, you could take animal liver cells or human liver cells and try and test your drugs on them. And the problem with doing that is that the liver cells lose what we call their phenotype, or they stop acting like liver cells very quickly. If you go look further down on this list, you'll see that the gold standard really is whole animal models, so rodent models, mouse or rat testing. And we know now through a variety of sources that animal models are not good models for human liver. So the animal liver and the human liver are very different. So what we've been interested in is coming up with an engineered tissue of human liver in vitro, as I'll show you in a second, in a multi-well format that you could try and use in drug screening. So we got into this actually because we were interested in engineering liver tissue for very different reasons, and I'll sort of take you on our journey because I think it's really instructive. We were interested in making liver tissue for therapeutic applications, and we're still interested in that. And the main application that we're interested in is shown over here, where people are working on extracorporeal devices. So these are out-of-the-body devices. They're, for, let's say, for discussion, dialysis-like cartridges, but they would contain liver cells. Okay, and historically, clinical trials in this area have been very disappointing. And the reason is the same reason that I described to you earlier, and that is that the liver cells in these devices lose their function very quickly. This device, therefore, does not perform liver functions, and it can't support patients. So we got interested in that problem. And as it turns out, if you can make liver tissue for therapeutic applications, there are probably other applications of interest as well. So the two things that we work on in my laboratory that led to this project are where one would get liver cells, and I'm not going to say really anything about that tonight except for to say we're very interested in stem cells as sources for liver cells or hepatocytes. What I am going to talk a lot about is this problem of the instability of the liver cell or the hepatocyte, and how one might go about stabilizing their liver function so that they could be useful both for therapeutic and drug screening applications. So if you think about this, sort of think about how nature does it, this is the architecture of the liver in the body. And my point in showing you this is just to show you that it's complicated. It's really complicated. It's actually, if you think about it as a chemical engineer, it's a beautiful mass transfer bioreactor, and I won't really go into details about that. But the specific things that the cells see in the liver are listed here on the left. And our approach has basically been to look at each of those, interaction with neighboring cells, interaction with molecules like extracellular matrix, interactions with soluble factors in the blood, the three-dimensionality of the liver, and physical forces. Our approach has been to look at all of these one by one in vitro in the laboratory and see if they could be useful in stabilizing the liver cells. So what I'll tell you about over the next few minutes are just two examples on this list: cell-cell interactions and gradients of soluble factors. So let's start with cell-cell interactions. This is in data what I said before in words. So these are rat liver cells plated in the laboratory on a collagen-coated Petri dish, and what you should see over here is that they're losing their function very quickly. This is just one marker of liver function. There are actually some 500, but for the purposes of this talk, we're just going to be tracking prototypic functions. Okay, so if you look at these cells after a couple weeks, they look, you'll have to trust me if you're not used to looking at liver cells, but they look completely abnormal, what we call fibroblastic. You can't see their nuclei anymore, and they go on to die. In the early 80s, a French group reported this effect, which we call the Coculture Effect. And this is a very dramatic effect. And basically what they showed was that if you added another cell type to these liver cells, another cell type that existed in the liver, there's some 6 different cell types in the liver, or it turns out other cell types from around the body that don't exist in the liver. If you mix these 2 cell types together, you get recovery of this liver-specific function, at least for a couple of weeks. So we were very interested in how this worked and studying this and how to exploit it for both therapeutic and screening applications. It turns out the science of these co-cultures is very convoluted. All of the interesting variables are coupled. If you change one cell concentration, you change the other. So what we did was borrow a technique from microfabrication. So this is just a simple semiconductor processing technique, which I won't go through in detail, but basically, instead of doing photolithography to make integrated circuits, we pattern protein on glass, okay? And here what we've done is pattern extracellular matrix. This is collagen on glass. And what that allows us to do is go from cultures like this in the top right, where we call these a random co-culture. The red cells are the liver cells, and the green cells are the supportive cells, to these kinds of cultures down here, these micropatterned co-cultures or microfabricated tissues. So what happens is we get these spots on the slide, we put our liver cells on there, they only attach to those spots, and then we can fill in the rest of the regions on the slide with the supportive cell type. Okay, so you can go from these kinds of cultures to these kinds of cultures that are highly organized. And then you can ask, how does the organization of the tissue affect the function? So this is just an example where you can create lots of different tissues. These are the liver cells stained red up here, and these are the co-cultures down here. Each of these tissues has the same constituents, if you will. So this is like having a dinner party where every person is surrounded by strangers. And this one is where every person is with somebody they know and the strangers are far away. Okay, so the organization is different in the culture. So we do this experiment, and what we see, and if we look at liver-specific functions, if you just look down here, is that the function of the tissue is highly dependent on that architecture. In fact, this peak here is for the cultures where the liver cells were all alone and surrounded by supportive cells, okay? And if you actually look at one of these cultures, so this is a larger island, you look which liver cells are creating these proteins, you see that these cells here near the interface are the ones that are preserving their phenotype or preserving their liver-specific function. And if cells are far away from those foreign neighbors, they lose their function, just as if they were all alone. Okay, so I'm not going to go through the science of this. We're very interested in how this works, what molecules are involved, what are the dynamics, how the cells reorganize. For the purposes of this discussion, let me just say that it works, okay? And this is the data to support that argument. This is a 10-week co-culture now. And what I just want you to focus on are the left two bars are what happens when you have hepatocytes alone, okay? So they lose their function. The third bar are those random co-cultures, so those randomly organized co-cultures that I showed you. They upregulate their functions, but then they lose them again. And the far bar, the turquoise bar, is our optimized, our best pattern configuration for these cells. And what you see is that these cells are now stable for 10 weeks in culture. This is for rat cells. Okay, so we're very excited about this. We've characterized these a lot. And I just put this up for the biotech people in the crowd. I'm not going to go through it. We have a lot of data on these cultures. We've done this with rat cultures. We've done this with mouse. And what's important, I think, and what I'll show you next, is that we went on to do this for human, and we figured out a way to miniaturize this process. So we did this again with human cells, and the interesting and surprising thing is that human cells are completely different in the sense that they require more interaction with themselves. Okay? So there was an optimum in the geometry that produced the best effects. We've now done this to create stable human tissues that live for a month, and we've characterized them as extensively as before. Importantly, in the human case, if you randomly organize the cells, they never do as well as the organized cultures at no point in time. Okay, so these cultures are superior from the sort of current technology. Okay, so then we wanted to miniaturize this in a way that we could think about doing a multi-well screen, which is something that you would do if you had a library of compounds that you were trying to test. And we needed to change our technology from the technology I described before, which is a conventional so-called lithographic process, to one here, which is a soft lithographic process. So this is based on a polymer technique. So here what we've done is we've taken, this is a 24-well plate, and at the bottom of each of these plates, at the bottom of each of these wells is a little stencil. Each of these stencils, these are like grade school stencils. There's little holes in them. You can pour your protein on here, and the protein will attach to the underlying plastic. Then you can pull off this stencil, You can then put your liver cells on there. They'll only attach to the spots, surround them with the supporting cells, and now in the bottom of each one of these 24 wells, you have identical human liver tissues of the optimal architecture. Okay, so I'll show you two pieces of data. We have lots more on how these could be useful. So the one is that these might be useful for predicting drugs that hepatotoxicity or liver toxicity of drugs. So the classic thing to do to try and test this is take drugs that you know are on the market or have been pulled from the market and rank order their relative toxicity in this platform. So what we did is we determined what the toxic concentration was for 50% of the cells to die in this system was, and looked at a whole bunch of drugs ranging from cadmium, which is an EPA-listed liver toxin, to drugs that you and I take that are in our medicine cabinet all the time. So just for reference, so small numbers are bad. That means a very low concentration of the drug killed 50%. Okay. So you can see that, in fact, in our system, these drugs rank order, they fall out just as the human data in the literature suggests that they would. And in particular, if you look at these two drug pairs, entacapone and tolcapone, and these two over here, in both cases, the more liver toxic compound that was pulled from the market actually was more liver toxic in our human assay. Furthermore, what we really wanted to look at was this compound, troglitazone. So some of you in this area might know this was the Vioxx before Vioxx. Troglitazone was Rayleigh, which was a hypoglycemic, it was a diabetic drug. And if you'll see it's very toxic in our assay, and since drug companies have developed several analogs of it that are not toxic. So if you look over here on the right and you look at troglitazone compared to its less toxic, newer compounds, you'll see that in fact it shows up as the most liver toxic of the bunch. Okay, so we're very excited about this data. Because we have a stable platform, we also think we can look at chronic toxicity. So you could look at low levels of exposure of a drug repeatedly. Okay, not just a 24-hour time point. And that's something that you really can't do in other platforms currently. So this is an example of a very high concentration of something like Tylenol, acetaminophen. And you can see at 24 hours, actually, it's not toxic at all by this measure. But over time, toxicity accumulates. And importantly, at 24 hours, if you look at the cells in the microscope, and you can see them in our system, any cell biologists, and probably most of you can see that these cells are not healthy. So you can look at what we call pre-lethal endpoints. You can know that drugs are going to be bad even before they kill the cells. Okay, so those are two examples of how that platform might be useful in drug screening, and we have lots more ideas, and we're very happy to have just received some Deshpande Center funding to explore these ideas. So I wanted to just show one more example of a toxicity platform that you could develop based on mimicking the liver, and that is by looking at how soluble factors work in the liver. So if you just indulge me for sort of one more second of liver biology, this is the capillary of the liver sinusoid. And if you look at the liver cells along the liver sinusoid, you'll see that the upstream cells are actually different than the downstream cells. What I mean by different is that they're different in their gene expression, they're different in their protein expression, they're actually different in their function. And this is clinically important in something that we call zonal hepatotoxicity. So if you look at these two micrographs on the right, this is histology of a healthy liver, and you're looking at this is a vein, this central vein here. This is this liver after seeing a high concentration of Tylenol, which turns out to be hepatotoxin. Many of you may know that. And it turns out that only the cells in this local region die, only the cells in this zone die. We call that zonal hepatotoxicity, and right now there's no way to predict that in a human liver tissue. The reason the death is zonal is that the cells in this downstream area have more P450 genes, which are the drug metabolizing genes. And therefore, they produce a toxic metabolite only in those regions, and then only those cells die. So our idea was to see if we could compartmentalize cells like this in vitro by using at least one of the signals we thought were as important in vivo, and that was the gradient of oxygen along this capillary. So this is MIT. I have to show one model. I took out all the equations. This is a bioreactor. It's a flat plate bioreactor where we have cells on the bottom here in Coculture, and we basically designed it so that oxygen comes in and is progressively depleted as you go through. And we can control this very tightly. So we can create a gradient. So what we did in this experiment that I'm about to show you is we took mixed cells that came out of the liver. We put them in this oxygen gradient bioreactor for a day. And then we looked, and in fact, they compartmentalized. So this is a P450 gene that is supposed to come up in the downstream cells, and this is involved in glucose metabolism, and it's supposed to come up in the upstream cells. And then we took this reactor and we treated it as if it were an animal or a human, exposing it to a high dose of this toxin. Now you're looking down on this chamber. This is my last data slide. And what you should see, black is alive and light gray is dead, is that the cells in the upstream region lived and the cells in the downstream region died selectively. And they died selectively, we infer, because they had more P450s, because they were in a lower oxygen environment. Okay, so this is the first in vitro model of zonal hepatotoxicity that we know of. Okay. So that was a very large-scale bioreactor that's really not useful for people who have very little of a candidate compound, so we miniaturized this. And this is just a miniaturized microfluidic device where you could put a little bit of compound here, a little bit of buffer here. This is a dilution tree, and you create a dilution of this compound, and then that compound at that particular concentration would go over a little microreactor, each of these which had their own oxygen gradient. So this is 8 experiments in one. Okay, so those are 2 examples of how we can stabilize liver cells in useful ways for drug screening technologies. And the message that I wanted to give, which is a little bit broader, is that actually this interface of microtechnology and tissue engineering is very rich. The liver is not the only example of microarchitecture affecting global tissue function. And in particular, we're very interested in the so-called stem cell niche, which is probably sort of a microscale environment within which stem cells live. I showed you examples of cell-cell interaction and oxygen gradients and all the characterization that we did. And I just want to mention, too, we have some 3-dimensional models that we're developing that I didn't show data on today. So I wanted to take this opportunity to thank my group. And Alice mentioned we just got here, and they all left the beach behind, came to Boston. Winter hasn't hit yet, so I haven't yet heard the full force of the complaints, but I'm sure they're coming. And thank our generous funding sources. Thank you.
I think Sangeeta would be willing to answer questions, and then a little later we'll have a general discussion, but questions about her talk would be nice.
My name is Nick Disabama from the Boston Consulting Group. So that was very impressive, and really kudos to the creativity and the science behind it. My question is, where are you from the business, or the tie between the science and the business applicability of these items?
Sure. So we're just getting started. We've gotten this innovation grant from Deshpande to think basically about how to commercialize this over the course of the next year, and the plan is to make a prototype, to flesh out the data that we need, and make a business plan. So I welcome any and all input along those lines. Question?
Why does the 3D modeling work? Because right now you're working basically planar, right? Mm-hmm. Why would 3D be critical?
So our 3D work is actually the project that we have in the lab for making 3D liver is to make implantable 3D liver. And the reason we're interested in 3D is that in vivo, for a clinical application, you need to get rid of the bile. And that architecturally depends on 3 dimensions. In vitro for drug screening, you probably don't need to get rid of the bile, which is why we've worked on these 2D models so far. So our 3D interest is really for the therapeutic application. Does that answer your question?
Do you want to say a little more about I found using a scaffold and then having the cells grow and thrive in that 3D scaffold to be fascinating for the therapeutic
application. Yeah, so I'm not sure which paper you're talking about, but I'll guess. So we've developed a technology for creating photopolymerized scaffolds within which cells are embedded. And we organize the cells in 3D because we think architecture is important with electric fields like dielectrophoresis. So you can organize the cells in 3 dimensions, and then since we're using a photopolymerizable system, we can freeze them in space in a biocompatible, degradable gel. And since we're using light, we can make a multi-layered tissue, much in the way that people rapid prototype using stereolithography. So we're at very early days in the project, but we've sort of done the feasibility for every one of those steps.
We'll continue our discussion afterwards. It's a pleasure now to introduce Joel Fink, the Thomas B. King Associate Professor of Material Science. Joel came to MIT and or joined the faculty in 2001 after doing his graduate studies in the Material Science Department at MIT. Joel's research interests are really fascinating, and I feel like everything Joel touches turns into gold, or at least it turns into a metal insulator semiconductor sandwich that behaves like gold. And he's recognized for his work with optical fibers, and in particular creating high-performance surfaces, mirrors, and such in the shape of hair-like flexible fibers that can be woven into cloth to reflect or detect light, radiation, and then can be incorporated into filters for telecommunication applications and other applications. He has done quite a bit of work on processing methods for photonic band gap filters, optical characterization, and some simulation and theory. Excuse me. Joel was recently awarded the National Academy of Sciences Award for Initiatives in Research in 2004 for his, quote, pioneering contributions and ingenuity in the creative design and development of photonic materials and devices. Joel's PhD work resulted in him co-founding OmniGuide Communications, a world leader in developing new optical transmission systems for telecommunication applications. I'm looking forward to Joel's talk. He'll talk about new efforts to overcome a barrier between processing technologies for electronic and optoelectronic devices. And he might tell us a little bit about some of the applications of these fibers for communications and maybe for non-invasive surgery. I'm sure he'll warn us if he's going to show those surgery pictures. The title is New Field of Multi-Material Integrated Fibers. Welcome, Joel.
So first, consider yourself warned at this point. Okay, so I'd like to welcome you all, and basically I'm going to be presenting some of my group's work on integrated multi-material fibers. The world of semiconductor devices and optical fibers have been separate to date. On the one hand, we have semiconductor devices which are enabled, their functionality is enabled by sub-100 nanometer feature sizes, the integration of metal insulators and semiconductor materials, and ultimately this enables a very high device density and sophisticated functionality. All this comes at a considerable cost because, in fact, processing steps and processing equipment that are needed in order to achieve these device characteristics are quite expensive. At the other end of the spectrum, we have optical fibers that actually are simply produced using preform-based fabrication techniques. Unfortunately, optical fibers to date have only been made out of insulators and actually have fairly large features which are incommensurate with device functionality. Now, wouldn't it be fantastic if we could, in fact, combine the world of semiconductors with the processes that we know of that are so efficient for producing very long lengths of optical fibers? And indeed, that is in fact what we've been working on. This is a cross-section of a fiber that actually contains metals, semiconductors, and insulators. This is a full-blown electronic device. It actually is an optoelectronic device in fiber form. Indeed, when we think about a single fiber as a device, when we combine these into a fabric, the fabric then has the attributes of a system. And so what I hope to convince you today, that we're able to in fact achieve sub-20 nanometer feature sizes in these fibers. These are cross-sectional features. We're able to integrate metal insulators and semiconductor materials, and that basically is necessary if we are to construct semiconductor devices. We're able to in fact realize optical, electronic, thermal, and thermal functionalities, and do this all on kilometer length scales. And so the vision here is twofold. First of all, we'd like to have or produce fibers that have the functionality of semiconductor devices, yet are produced using fiber optic or at fiber optic lengths, uniformity, and cost, and basically take these fibers and integrate them both within a fiber, a single fiber, put multiple devices, but then also weave these into fabrics that have the attributes of systems. And so here is an example of one such fabric system. This, in fact, is a functional spectrometer. So if you illuminate light on this and connect up the edges of the fiber, you could actually analyze, get a spectral analysis of the light that hits it. And you may notice from where you're sitting, this actually is thinner even than an iPod Nano. So the outline of the talk today, which I've been told is only 20 minutes, so I have to go through this fairly quickly. But basically, I'll give you some a description of how we actually produce these fibers and some of the theory behind them. Transition to an application, which is that of cylindrical photonic bandgap fibers. These are fibers that are being commercialized for medical applications. And then finally, introduce you into what we view as a very new and exciting world of metal insulator semiconductor integrated fiber devices. The problem we started working on when I was in graduate school was a very simple problem. And it involved answering a question, which is, how do we actually produce the most efficient mirror possible? So it's a very simple question. It turned out that the solution was not that straightforward. It wasn't apparent. So you could consider a strategy which involves taking highly polished metal and use that as your mirror. It turns out that a fraction of the light is absorbed because of the finite conductivity of the metal. You could consider multi-layer dielectrics. These typically leak light in transmission after a certain angle. And the question was, could you actually produce a surface that could actually reflect all of the light? Now, if you were able to produce such a surface, you could then use it to contain light. And depending on the geometry of your surface, you could actually trap light in a volume or along the length of a fiber. And that was the very first discovery that we made, which was, in fact, you could, if engineered correctly, you could, in fact, produce this perfect reflection from a simple multi-layer dielectric. Now, obviously, the layers here are a fraction of a wavelength of light, and that poses considerable fabrication challenges when we go and scale this up to very long length scales. And so, in fact, the first problem that the first application of these very efficient mirrors was optical fibers, in which we contain the light in a hollow core as opposed to the containment of light in an index-guided fiber, which is what typical optical fibers are doing. In fact, what we thought was that many of the fundamental limitations that optical fibers have would be alleviated if you could actually propagate light through a hollow core. Light reaches the Earth from the sun, travels many millions of kilometers without significant attenuation, and therefore we would expect the attenuation through a hollow core to be significantly lower than that of a material. The challenge, though, was that of fabrication. How do we put together a structure that on the one hand has layer thicknesses that are 100 nanometers, and on the other hand is kilometers in length scale? This is to give you an idea of what the dimensionality disparity here. It's like drawing a structure the thickness of your finger, extending it from the Earth to the moon. That's what we're talking about here. And so what we developed was a set of material compatibility criteria and material selection criteria. And what you need to have is very large index contrast in order to achieve omnidirectional reflectivity. The materials need to draw at the same temperature, so that imposes some restrictions on viscosity. You need to prevent capillary breakup. Two such materials that actually follow those conditions are amorphous semiconductors, also known as chalcogenides, and high glass transition polymers of the like of Kapton or polyether sulfone. What we then also did was develop a fabrication technique, which is actually just a roll-to-roll technique where we take a feed of the polymer, evaporate the semiconductor on it, roll this up into a preform, and then draw it into a fiber. And basically, this is what the result is. We have a fiber that has this multi-layer dielectric, has this photonic band gap that is omnidirectional reflecting, confining light now in a hollow core. And the beauty of this is that you could now decouple the problem of transmitting light from the problem of finding transparent materials. Because light, in fact, is contained not in the material, but in the hollow core, and the materials themselves could be almost opaque. So the first application is actually that of non-invasive surgery at 10.6 microns. The idea is to take laser light coming from a CO2 laser, which is in fact readily available in medical centers, instead of sending light in order to treat and remove growths from the patient's lungs or airways, basically using a handpiece and a line of sight technique. What we're going to do is couple light into a fiber and guide it through an endoscope right to the point, remove the tumor in that way. And as Alice warned you, this is in fact the video. This is the airway of a patient who is awake, has papillomas in her airways. Here's the first papilloma that's being treated. This is the tip of a fiber, a little over a millimeter, going down through the nasal canal into the airways. There's about 10 or 15 up to 20 watts of CO2 laser energy that's going through the fiber and basically ablating the tumor. Now, this procedure was carried out by Dr. Jamie Kaufman at Wake Forest in North Carolina, and since then there have been a full FDA approval, and procedures have been carried out at MD Anderson Cancer Center and actually today in Long Island. So the idea here, from a business perspective, as a gentleman who just asked, is to create a product that's disposable, and so the revenue is tied to the number of procedures. To give you an idea, there's 1.2 million pulmonary procedures annually, and so you could actually, at least in principle, sell a fiber for per procedure. The typical duration of use per fiber is about 5 minutes of on time. Price is going to go anywhere between $200 and $800 per procedure. A short length of fiber, ability to tap into installed base of lasers. There's about 20,000 surgical CO2 lasers already in hospitals. And so basically these fibers are going to couple to that installed base, and it's compatible with commercially available endoscopes. Since that work was actually published 3 years ago in Nature, we actually went on to construct fibers at significantly shorter wavelengths. Here's an example of fibers that conduct light not only in the infrared, but down to the visible and even in the UV. What you could see is we've gotten much better at putting many, many layers here. This is a section of the fiber, and actually the layer thicknesses are very, very reproducible. In fact, if you consider what we have here, it is just an annular cavity, and in that sense, if you put in a gain medium into this fiber, well, then you will have optical feedback, but the optical feedback is not going to be in the axial direction, but in the radial direction. And what you'll have here is a radial surface-emitting fiber. And so here's what we do. We take a fiber. It has this mirror cavity. We fill it up with the gain medium, pump it, and get lasing lines. But the lasing lines now are not occurring along the length of the fiber as normal fiber lasers would, but in fact in the radial direction. What is this going to be good for? We're not sure, but one of the applications could be to deliver illumination for photodynamic therapy. In that case, the very thin polymer strand goes into an artery, and basically you then pump your light through the fiber, guides light, it hits this little plug where the gain medium is, and you laser radially, so you could illuminate the surface of your artery. Another application could be, in fact, in clothing that emits light, lasers in. Now, we have also shown that these thin layered structures could go not only surround the core, but could go around the lining of the fiber and actually produce fabrics that have share many of the characteristics of very high-end telecom filters. just now you're able to do it and incorporate it into fabrics. This is an example of a single-mode Fabry-Perot resonator. This is the hallmark of a resonator. It is a sharp transmission line within a region of high reflectivity. Finally, let's spend a few minutes on metal insulator semiconductor devices and basically take whatever we've done till now in terms of materials, namely use a polymer and a semiconductor, and add one thing to it, a metal. If you get these three materials to draw down from a preform into a fiber, well, you have a functional semiconductor device. And that is, in fact, exactly what we've done. So here is the fiber. This is a cross-sectional SEM. You illuminate it with light. You bias the electrodes. These are where the electrodes are. You excite electron-hole pairs. That changes the conductivity of the fiber. And basically, you have a photoconducting photodetector. What's really interesting about this photodetector, it's a line. And this line could be hundreds of meters long. And so if you then illuminate a particular section of your fiber and watch the currents coming out of the edge of it, you could detect that your line or fiber has been illuminated. What it doesn't give you is a straightforward way of knowing where you're being illuminated. And in that sense, there's a simple solution, which is that of a grid. And so when you assemble such a grid of photodetecting fibers, it should appear like the bug screen on your window. Well, you get a photodetecting mesh that is flexible, transparent, and could cover very large areas. And what I'd like to do then is to point or call out to your attention what in fact a lens does. What a lens does is it's an analog computer. It takes an incoming ray and maps it to an outgoing ray. If you place two such photodetecting grids, those two photodetecting grids could detect not only a point of illumination, but the vector of illumination. And hence, your lens transformation, which occurs in real space in an analog fashion, depending on what your lens is made of and the curvature of the surface, can now be performed digitally. You could, in fact, create and emulate the lens functions, some of the lens functions, in the absence of a lens. And the implications of that are far-reaching because we know that optical systems, from your eye to the camera to a telescope, are in fact limited by the size and the fragility of the lens. So this is a video that does not need a warning beforehand. It's actually quite benign. What you just saw there were two grids, photodetecting grids. They're hooked up through a USB port to this computer. Here is a mag light over here. It's illuminating the two grids. And this little system here is able to discern the direction of illumination. The nice thing about this is that the number of fibers that you need actually scales like the square root of your resolution. So in fact, if you need a megapixel resolution, you only need 2,000 fibers. 1,000 in one direction, 1,000 in another, it creates 1,000,000 crossings. Your resolution goes like the fiber crossings, not like the number of devices. So this is what enables very large area coverage. What we'll now do is take some of the concepts that I discussed before, that of a photonic bandgap and a Fabry-Perot resonator, combine it with this photodetecting capability, and basically what that leads us is to the little fabric spectrometer that I mentioned before. Each one of these fibers now is not a broadband detector, but actually a narrowband detector, where the wavelength of detection is in fact controlled by the layer thicknesses and by the thickness of the optical cavity. So this was work that was published in Nature about a year ago. And we've since also started making fibers that are also integrated devices. So there's not only a single detecting layer here, but multiple detectors and up to 8 different devices in a single fiber cross-section. When you realize that your device is now in fiber form, you need not consider only planar objects and planar functionalities around particular axes like a lens has, but in fact consider now 3-dimensional objects that could in fact detect light coming from any direction. And in fact what we've also recently shown is that a sphere like this could detect light coming from any direction, and in principle could also take on some limited vision capabilities. So this is work in progress, and in fact was recently submitted for publication. Last but not least, I'd like to conclude with saying that we need not consider only photodetectors. Here's an example of a thermal detector. In this case, we're actually touching a grid of such fibers, viewing it with an infrared camera at the same time. And what you can see here is that the information from the infrared camera and our thermally detecting grid is comparable. Obviously, the camera carries a greater resolution. Interesting thing to note here is that a thermal camera is about a $40,000 perspective. These thermal grids are obviously well below. So anyway, this is the final result that I'm going to briefly mention, which involves creating transmission fibers that also have some detector structures around it. And the basic idea here is to create integrated fiber structures, in this case, a fiber that could transmit light and also tell you when it's about to fail. And that becomes important when you start considering sending tens of watt of laser power through patients' airways, but also for other types of applications. So this work is actually going to be published shortly in Nature Materials. With that, I'd like to end and thank a very, very fantastic group of students and postdocs, collaborators, and some of the funding agencies. I also thought it would be fitting in this hall to thank Rayleigh, who not only enabled this very beautiful building, but also was a very strong and avid supporter of the technology that I described way back in the year 2000, where the only thing we had was a bunch of slides and a big dream. So thank you very much. Yeah, questions?
Is there any way you can maintain the coherence of the beam as it travels through the fiber? Because if you can use basically use interferometer and to detect where the light is basically being shined on the fiber with a 2D array.
Yeah, these the beam should not, when it travels through the fiber, and if the fiber is supporting a single mode, it should not lose its coherence in that respect. And moreover, the lowest loss mode of this fiber is actually a non-degenerate mode, and in that sense, you have a very, very clear idea of what the polarization state is at the exit. It is a TE01 mode, so I didn't get into that, but the answer is absolutely.
Grandma from the Snow School. I'm very interested in the process of the weaving process. What kind of like loom you use to manufacture this fabric?
What kind of weaving?
Yeah.
Hand weaving. Not hand waving, hand weaving. Very different, but basically, this was done by Mehmed Ben-Dir, and actually I think also his wife Esra helped in this. So they worked on this together and just wove it together. I'd like to say that eventually, as we get better and better at making these fibers, there will be weaving challenges that need to be addressed when we want to get these into cloths. And in fact, there are some programs now that are going to be addressing that question exactly. How do we really get this into clothing and cloth? Absolutely. But there's no good answer to that other than by hand right now.
Can you talk about the sensitivity of the photosensitive fibers? How low light can you go?
Yeah, these are yet, we haven't done careful characterization of them. I mean, what you see there is on the level of a mag light, which is not a very intense speed. For the thermal fabrics, actually, it's enough to hold your hand about half a meter above it, and it senses the radiative transfer from your hand. So that actually is quite sensitive. But what you're asking for is significant data on that. That actually is being measured now. And part of the complexity is that there's a whole range of semiconductor compositions that one can tune here. So That, I don't have a good answer for you yet.
Suppose instead of having a beam of light that you shine at the screen, you actually have a point source like a candle. Is it possible that in the future you'll be able to create a screen that will show you where the point source is?
Okay, that's an excellent question. In fact, the paper we submitted, what, you want me to repeat it?
Or make it
Okay, I'll repeat it, hopefully the spirit of the question.
Can you speak for the podium, please?
Yeah. The question was if I took a candle or a point source, and I'll extend that to an arbitrary intensity distribution, could you in fact discern where your point source is? That was the question, and I'm going to go beyond that. Could you in fact extract the image? The image of your object that where the light is emanating from. That is in fact what we tried to do and demonstrated in a limited capacity in that publication that Dr. Aburadi from my group just submitted. Basically what we showed there that if you have two such screens, and right now what we're doing there is we need to impart a certain motion to them, but that is not necessary. If you have two such screens and you're able to get an arbitrary intensity distribution on one and on the other, what that enables you to do is to calculate your phase. Once you have the intensity and the phase of your incoming field, that in principle should enable you to back propagate your object. And that is exactly what this paper is about. It's about how far can you go in lensless imaging. So I'll definitely be happy to provide you with the manuscript.
I'd just like to close by saying Yoel is my poster child for how the support of fundamental research can lead to innovations in very unexpected ways. And this problem he embarked on was a thought problem by Lord Rayleigh from the 19th century on multi-layer structures and reflectivity, and funded as really a physics problem. And to be able to revolutionize a form of surgery not too many years later, I think, is a real tribute to the kind of work we do at university and the great innovations that can come from very basic work. And as squeamish as I am about the movie, Yoel also didn't give himself full credit. They were allowed to do that surgery, as I understand it, before FDA approval because it was a very serious case. And normally the patient has to have their jaw broken in order to get the straight shot laser in. And so this is certainly revolutionized type of surgery, not just added another tool to it. So thanks. Now it's an additional pleasure to introduce Professor Timothy Swager. He's the head of the Department of Chemistry and the John D. MacArthur Professor of Chemistry since this summer. Tim came to MIT in 1996 after completing his PhD in chemistry at Caltech. I got to work with Tim as he was the Associate Director of the Institute for Soldier Nanotechnologies for its first 3 years. He's also the recipient of many awards, among which is the Carl S. Marvel Creative Polymer Chemistry Award, awarded this year. Tim is recognized for his work in several areas of polymer chemistry, in particular his pioneering work on ring opening metathesis, polymerization, and his contribution to the understanding of conducting and semiconducting polymers. Now, we all know what metathesis is now after learning about it because of the 2005 Nobel Prize in Chemistry. One of the recipients, of course, was our own Dick Schrock, and another one was Tim's research advisor, Bob Grubbs. He's also recently been carrying out groundbreaking work on chemical sensor technology, such as the chemical detection of explosives and improvised explosive devices. He's the scientific founder of Iptix Corporation in Cambridge. That's a company focused on organic dielectric and electro-optical materials, and molecular mechanisms in Cambridge, a company launched to develop technology for muscle material close to human muscles. He's been involved in a consulting capacity with Nomadics, an Oklahoma-based company which has licensed his work on explosive detection and is deploying it in Iraq. Today his talk will be on novel molecular designs as the future of new materials with technologically useful properties. I think we will enjoy this chemistry lecture on molecular architecture, the ultimate control of soft material properties. Welcome, Tim.
Yeah, thank you, Allison. It's a pleasure to be here. And in preparing for tonight, I decided to do something a little different than maybe my usual research talk. I'm not going to tell you about sensors, which is probably our most mature application, but I feel when you have a group of people always looking for the next business advantage and the future, that I would like to share at least kind of a vision I have about that what we can do with chemistry, which I don't think that is always the way you think about, particularly in a materials company, formulating your company strictly around a molecular structure, or what I would call a privileged molecular structure. And so I wanted to have kind of an evangelical thing as a synthetic chemist. I start with my colleagues watch me, usually an engineer. When I'm bored, I start sketching reaction schemes and start scheming the next things I want to make. But anyway, I'm going to give you a snippet of how I like to think about molecules, and maybe some of the applications are down the road a ways. But anyway, just give you an idea of how we like to think about this. And part of the motivation, in terms of, at least, or if I want to try and hook you into my scheme as to what this is about, is to try and maybe convey that I think there is a strong basis for starting companies. There's very often when you talk to patent attorneys, or at least when I talk to them, they say, oh, composition of matter patents, that's gold. That's what you want. Well, composition of matter is getting more complicated. I mean, there's Joel Finks that can figure out innovative ways to put things together. But in many areas, and just in polymer design, it's getting very difficult. There just aren't that many types of monomers out there that people use, and there are so many ways you can put them together, and it starts getting complex enough with only thousands at tops of monomers that are really available to you without a lot of molecular design, to come up with ways to really uniquely differentiate your intellectual property. And you may have freedom to operate, you may get that, but you might have some difficulty down the road with somebody coming in and squeezing in on your turf. And so what I'd like to convey tonight, I think, is that with molecular architectures that can give you unique properties, just fundamentally unique properties, and if you can define what it is in that architecture that makes that unique property, that's a very important way to look at how to define intellectual property and potentially new companies. And starting companies around a molecule is maybe for pharma is not new stuff, but in materials, I don't think it really has been done a great deal. And I think that a big thing that's really come about that is helping this is that nano word that, Alice is now a nanoscience scientist here, but is that it also with nanoscience, I think there's appreciation that small amounts of material can be in very, high value capacities can be enabling, and you can make a business around those. So we can start thinking beyond that 1,000 monomers that are out there that are cheap and you can buy tank cars of, and start looking at new applications, at least to get a foothold on new markets. So today I'm going to spend most of my time talking about what I would a molecule that I would say is a kind of a privileged architecture in my view. It's been around since 1940s. It was first synthesized as just its native self. It's called tryptosine. It has 3 aromatic benzene rings that are hooked together. Incredibly stable molecule. It is shape persistent. It is a propeller. has 3 dimensions. It is not compliant whatsoever. And I'm going to show you some vignettes on how you can use this molecule to design new materials, how you can apply this simple molecular shape if it's hooked into the molecular structure properly. And one of the things is to actually couple the way the polymer orients or a molecule orients with respect to this propeller. You just can't hang it on anyway. You have to actually fuse it into the backbone to where its direction is coupled to what you're trying to direct. So I'm going to give you some examples of this here today. And one of the key features of this molecule that I'd like to draw your attention to is obvious, but it is really 3-dimension, and it has width and height, and it's different than a lot of other, electronic molecules or aromatic molecules that you might run into, which are often flat, or at best you can have them bent. But when you have this 3-fold structure that has width to it, when you try and pack this into a solid, you cannot pack it in a completely dense framework. At best you can do is to consider this, if you were to make a 3-dimensional object, essentially a trigonal prism out of this, and pack that densely. And that gives rise to free volume, that is free space within the molecular structure. And in general, molecules don't like that. There's a cliche in chemistry that nature abhors a vacuum. That is, molecules like each other. They come together. The reason that they stay together in condensed phase is they're sticky. They hang out together, whether it's just dispersion forces between coupling of the spontaneous dipoles or hydrogen bonding, but they generally like each other. And so if you have a molecule and you like this that tends to promote free volume, and you put it into another material, it will do everything it can to minimize that free volume. And so if you take a molecule, an elaborated tryptosine, I won't show you any synthesis today, but again, this is what we do most of our work cooking in my laboratory. You take a elaborated tryptosine like this and put longer wings on it, and if you dissolve it into a liquid crystal where the liquid crystals are spinning around so they map out a shape that looks like a cigar, the liquid crystal will align, the molecule will organize in the liquid crystal such that the liquid crystal threads through that 3 volume. And that's a way of aligning molecules. We found that you can align very large molecules that are contra to their aspect ratio, which is something that hadn't been done before. But using free volume is more important in the alignment than the actual aspect ratio of the materials, which usually, you think about, if you throw another stick in here, it will align with the liquid crystal. You throw a stick where you pose the free volume directly, diametrically opposed to that axis, and the free volume will win. It also works in polymers, again, where the polymer chains tend to thread through these free volumes. So these are the way these materials, fundamentally, they're driven by thermodynamics to organize this way. And I'll show you how we can use that in a variety of different ways. And so one of the first little trick slides I have is I like to show this to physicists in the liquid crystal area that think they always know more than chemists when I talk to them. And at some level, in some aspects, they do, but this is one where I've never got a physicist, they know I'm trying to trick them, but they just can't bring themselves to rationalize, how this structure could possibly align in a liquid crystal solvent better than that one. This one's long and skinny. It should fit. This thing has this ugly wart on the side of it that will only disrupt its organization. But if you take it, these molecules are chromophores, and so very easy to monitor how well they align by just doing absorption spectroscopy. And you find that the red molecule aligns better because it has this little stabilizer wing on it, and things are threading through it, and it's feeling its surroundings. So it's like a compass needle inside this liquid crystal. And it actually is looking and knows which way to direct, although the liquid crystals are fluids, so they have essentially mosaic of orientation. They have one global director, but locally they're very disordered. So you can do things where you take these molecules, and this is something we did in collaboration with a company in Switzerland called Rayleigh, and they actually use a photo alignment to write images into materials, and we put a fluorescent green dye in this, and you can see that when you what's happened here is they've taken essentially an optical using an optical orientation in the liquid crystal simultaneously with polymerizing it. They've been able to write this image. Now, this image is not that fine because the liquid crystal is being polymerized. It has a very weak field that's aligning it, just an optical field, and you don't get a high resolution image out of that. But you get a high resolution just essentially in a refractive index sense. But because we put a dye molecule in it, which says, okay, you might be going this way, you might be going that way, but I know I'm going to look on average, and I know which direction to head, you get a higher resolution image out of this. And so this is a way that you could make something that might be a security badge. This is only read in fluorescent mode, and the going from the negative and positive image was just the rotation of the polarizer that you're looking through this. So that's what you were just looking at in that movie. So that's one application of this. There are many ways to do this. You can think about ways in terms of brightening your liquid crystal displays this way, throwing in a little magic pixie dust. So one of my main schnicks in chemistry is working on electronic polymers. So one of the things that we like to do, and this is if there is overlap with my sensor life, it's in that we work with molecular wires that amplify sensor materials, sensory responses. And one of the things that we're always looking for is ways to en masse put wires between electrodes and having them isolated in this way. And the problem is generally polymers, when they're soluble or if they're not ionic and so they have big repulsive interactions with themselves, then generally they're coils. And when you try to straighten them out, they crystallize and they crash out of solution. And so we were looking for ways to do this. And the thought was, can we now use this same functionality that creates this unique interaction with its environment, put these tryptosine groups onto a polymer and use it to straighten out? And liquid crystals, of course, are wonderful to align in electric fields. That's the reason these laptops work here in front of us. The liquid crystals can be redirected with those electric fields. So we set out to see if you can do this. We've done this on a variety of different materials. This is just a very simple visual example of how this works with a polymer. These are polymers that are often used in light-emitting devices. But this is one that's just with an optical illumination. We have a black light that's illuminated. This is just a liquid crystal test cell. Without a potential on it, the molecules are aligned in the plane of the screen. When you apply a potential over these little pads that are defined by indium tin oxide, the molecules rotate out of the screen and they're pointed straight at you. There is no, essentially, transition moment in the plane, so the molecule cannot absorb light, and therefore it can't emit, and that's why you see this as going dark. So you can do this, this is not, a device that you would want to make in anything, but we've been able to extend this to create molecules that have more sophisticated architectures, such as this, and it can be very high molecular weight, and they have extremely high dichroic ratios. That is the ratio of the optical absorption parallel to the director of liquid crystal versus perpendicular. And we're up at ratios around 24 here. It tends to increase with the molecular weight of the material. And these molecular weights here, we have molecules that are microns long. A micron long molecule that is completely stretched out and it's in solution. And so now we're looking at ways you can gel liquid crystals, create these little micro trusses that go through a liquid crystal media to actually stabilize a device. And one of the things I say, the liquid crystal devices are rapidly evolving, not a static technology. And it's been driven by all these other competing, plasma displays and OLEDs and PLEDs. And so they're not going to go away. And there's still a lot of room for improvement, and particularly with aligning molecules like this. Now, one of the other things I like about this in terms of my electronic life is that when we put these molecules in liquid crystal, you can see that there's a spectroscopic change. These two, the red and the blue, the green and the blue trace here are in solution in thin films. But when we dissolve the polymer into a liquid crystal, we get a different spectra. And that spectrum is because of the fact the molecule has a very long planarity to it, and that gives a greater electronic coherence along the molecule length, and that is good for doing molecular electronics. That is what you would like. You would like your electrons to be able to just whiz through it. There's essentially one coherent state across your device, and this is what you would like for devices. And again, we can make devices that have very long molecules and sometimes very short. molecules. So that's just a bit of a future. So now what else would we like to do with this free volume? I mean, we have lots of things we'd like to do with it, but one thing we would like to do is essentially nothing. And what do I mean by that? That is, we would like to make things that do not respond to electric fields or respond minimally. And I think you all, any of you that are familiar with the semiconductor industry, know that there's a big need for low dielectric constant materials that have the right structural properties for semiconductor interconnects to try and keep wires from, essentially in your circuits from talking to each other, so you can get rid of those capacitive delays. And, it would be great if we could do it with vacuum, but vacuum is not a very good structural material. We need something that's a little bit better. Most of the ways that people have done this with soft materials is they've made Swiss cheese. You take other materials and that are stable, and you pattern them and you put pores in them. Problem when you make the Swiss cheese wholly enough, often the mechanical properties go down. So that doesn't seem to be a winning solution. What we can do with a molecular architecture like this is we can make a very rigid material, something that has modulus it's very hard, something that, ideally to get it inserted into fabrication processes, it has to behave like silicon dioxide. Everything was optimized around silicon dioxide. You want to insert it, you want to give them something that looks like silly putty there, and you're not going to get there. In fact is, when I talk with semiconductor manufacturers, they're more interested in mechanical properties than the dielectric constant. If you get the mechanical properties right, and you have at least some idea how to get the dielectric constant right, they'll be very interested. So what we're after here is how we create a molecular architecture which intrinsically has a low dielectric constant by, at a kind of molecular level, constantly at every unit inserting free volume. And we've done that with a series of materials based on these iptosine materials, these essentially tryptosine materials. Again, we fuse them across ways so the molecule cannot just rotate independently. People have put bulky groups off the sides of polymers before, and it didn't work. This is a case where we use a rigid backbone that's actually a little too big to thread through here, so we keep that free volume up. And these are materials that, again, have good, and this is just one of our early examples, has a very good dielectric constant. It's very hard, and it can decomposes, around 500 degrees centigrade. That's very tough for organic. I always get my inorganic colleagues or people in inorganic materials always tell me the problems with organics that are not stable. 500 degrees is there, and its glass transition temperature is over 500 degrees. That is, there's no segmental motion of the polymers because of this big group that would have to wing around. And it's completely soluble. And those are parameters I don't know how to get in any other material like this, to get solubility and those kinds of high class transition temperatures. And so we think that by doing this, we've been able to engineer in essentially a unique set of properties. And again, that's why I call this a privileged structure. It tends to give us things like that. Now, other things that we're interested in have to do with mechanical properties of polymers. And this is an area that we collaborate very heavily with Ned Thomas in material science. And I was inspired by listening to DuPont talk about Kevlar, and people talk about ballistic materials. And Kevlar has a very high modulus, but Kevlar, actually if the fibers can't slide past each other, it fails. And it's because it's a woven structure, and if you shoot it, this is not the outer layer, but if you shoot a Kevlar vest with a bullet and you look a few layers in, you'll see that the bullet was only maybe deforming here, but you can see the stress of those fibers was distributed. And it dawned on me that I work in a wood shop, and if you get glue on your clothes and you let it dry, what you find is your clothes tend to rip real easily where that glue was, and that's because any strain is localized and it rips the fiber. So we thought, Kevlar has very strongly bound polymer chains together to it, hydrogen bound together. What if you now create a fiber where the chains at a molecular level can slide by each other a little bit, but because they have essentially this threading mechanism, they can't slide indefinitely because you'll get some locking, you'll get load between the different polymer chains, and if you try and spline them, they're going to be all locked, interlocked, and interconnected. And what kind of properties can we get out of that? Well, we found that that it's a very robust design principle, and it seems to work pretty well. So this is a polyester we made that has none of this tryptocene in it, the exact same molecular weight, processed the same way, same thickness with the tryptocene, much stronger material. That's not exactly an analytical study, but that was something, that was actually the story of this is I went in the lab and I saw this and I said, this is great, we got to get a video. I said, go around, I'll pay for a manicure, get somebody to, have a nice hand model, and I get these gloves. And I said, why do you do this? Well, it might be toxic. I said, polyester, let me eat some of that. And I was going to eat it, but they wouldn't do that. But students these days. Okay, anyway. Here's what the structure of that same material looks like. And it has a tryptocene in it. You can just eliminate the tryptocene in this. The tryptocene is relatively dilute. The monomers are in different ratios. And here are the actual stress strain curves here. And Ned and one of the things that's really nice about this is we can get a material that's more ductile. That is, it stretches longer, has higher strength. You've been able, again, to get a series of mechanical material properties that aren't necessarily always commensurate with each other in this. So you can get initial yield strain, and then you get some plastic deformation, you get strain hardening here, and we get a failure. And this is what you get without the tryptocene. And this is on many materials. We have multiple material sets there where when you put a tryptocene in it, multiple architectures, you enhance the properties. Now, I like the wilder structures, the better. So one of the things I'd like to get rid of that polyester and make only tryptocenes that have crazy architectures like this. And it's random because of the way we can't control exactly the way the chemistry comes together, something called stereochemistry. But we're very interested in these types of materials as essentially ways to mix, and we're involved in this. We have some early results on it. We don't have mechanical properties, but we show we can do this, where you can now start taking these large two-dimensional materials and dispersing them in polymers and having polymers thread through them in different ways. And lots of ways we're looking at this. One thing I would like to do is figure out how to control that and essentially weave at a molecular level. Can we take two molecules, one that way, and weave a polymer the other way? Can we make fabrics at molecular levels? But there's also other interesting things we believe we haven't done this yet. These are more theoretical ideas, but other ways that we think we can do neat things with these structures to form things called negative Poisson's materials. So if you take a material, usually you stretch it, it usually densifies a plastic, and because you're stretching the chains out and you're giving them more order, and so you get a contraction. But if you have a material, for example, that when you stress it, you increase the amount of free volume in it because you've engineered that in, you can essentially open up space and have it stretch. And that has great implications for many materials, things that you can't imagine. But the first thing would be ballistics. If a bullet's hits something and it needs to deform rapidly, you create free volume and it pushes back or it hardens. And so there are interesting things that you can do with this. Now in the last little part, I thought I would tell you about another privileged structure that we're interested in. I don't have as many slides on this, I promise, but it has to do with a molecule called Coculture. And this is an actuator made on polypyrrole from the Ian Hunter's group, and this is just essentially they're mocking up a hand here. It's not, they have much faster ones now. They haven't made the whole hand out of the faster ones, but they're just little actuator strips here that are essentially making those fingers move. But we are interested in taking actuators and at molecular levels, designing in hinges and complex mechanical motions in molecules which can give rise to stronger, faster, larger responses. And our favorite architecture is something called Coculture here. And it's very simple. It's very similar in composition to the first thermoplastic era, which is Bakelite. And it's formaldehyde and a phenol. And so it's cheap material to make. There's a lot of chemistry around these, and it has complex conformations. You can flip them around, but these molecules behave like hinges, and I'll show you here in a minute. And so what we're working on is ways of putting these and putting electroactive units in these, and we postulated, and we've made polymers of this nature, and postulated originally that and we're working on these actuators. We don't have them working as well as polypyrrole right at the moment, But the thought was that based on just some back of the envelope calculations or theory for me, I found that if you take these and you take an electron out of it, they should want to fold up. And in doing so, these other rings move. And in fact, this has been demonstrated computationally by another collaborator in Material Science Department, Nicola Mazzari. And what he did is in silico, he started out with my oxidized molecule that was coupled, and then he put an electron in it and showed that it wants to open. This is a full quantum calculation done essentially in real time and letting the structure relax when you can do this. And one of the things about this, when this molecule was connected there, not only did we have mechanical linkage, but we had formally was an unconventional, though, but a chemical bond between those two structures. And that can give you a lot of force. And so that's something we're very interested in. So I just want to wrap up again with my stump speech. If I sound like evangelical here, it's on purpose. But it's also a deal. I mean, I've talked to people about starting companies before, and I think they're often, I feel like I'm wearing, have two heads or something when I'm telling them about how you can take a molecular structure and essentially define technologies based on a molecular structure. I think it's important that the structure is right. There are lots of things that you have to be able to do with it. And one of the things I think in starting small companies you have to be aware of is your customers are often industry. Intel is not going to buy low-K dielectrics from a small company. They're going to need a big manufacturer. They're not going to base a process on it. And so there's going to have to be partnering, and I think the technical metrics get very, very, very dicey in very early stages of a company because of this, because you're going to deal with companies that have tried and failed many times to do something just like that, and you have to convince them that you've done it. And that's a challenge, but it's something we want to do. You have to also think about what you can do with chemical synthesis. I mean, it really implies you really have to have chemistry. And one of the things I will say that I think that is important about the materials area, particularly very high value materials, and maybe just stop with that, is that you really need to seek out customers with challenging problems that need that extra special sauce, we would say, or spice to put in something. And often they come with from the Department of Defense or Homeland Security, and a couple markets that I'm very active, in terms of my research. But I think that those are very good customers, and they're going to drive a lot of these technologies in the future, and help us to push some of these things further. So with that, I'll just stop and thank you for your attention.
I'm sure Tim will answer questions. Before we let him eat his polymer, we're going to run it through Sangeeta's chips and check its liver toxicity.
Oh, I would survive. My liver's shot anyway. not from eating polymers. Lead it.
Typically, companies with core technology, a platform technology, in search of problems, have a lot of trouble. And they usually bumble along until they find one killer app, and then they become a killer app company, not a platform company. Mm-hmm. So the question is this platform and identifying applications, should it be a company or should it reside in academia and then spin off as each killer app gets it?
Yeah, I guess that's definitely a very valid point. I don't either. It's something I struggle with, where you can paint this picture, and then at the end of the day you have to say, where are we going to just let it hang out and make something work, right? And rather than diffuse yourself and chase SBIR grants on 5 different topics, and I agree with you enormously. And I'll tell you, if I could get large money for low-K dielectrics, I would forget about everything else for a while in this company. But I mean, for example, everybody's very gun-shy on low-K dielectrics, even though it's, you know, projected to be this huge market, and it's one of these things that the semiconductor roadmap just keeps missing the mark on, because they're, you know, nobody has a solution to it. They keep saying we have to have this, and then oh, that's not there. Let's figure out a way around it. But I agree. I mean, that's you know, it becomes a little bit of a, you know, maybe a company becomes what we might call a holding company, where you have IP and you try and, you know, spin it out, or but you try and get it through that initial phase to get it up to it's enough. Where I have as an academic is my students lose interest far too early in a project to shepherd it to that level, to where, you know, the risk for a big company, for example, a huge company, to come along and say that's risk adverse, that you know, their venture arms will typically not go into a first round or something.
No, I wasn't thinking that. I was thinking more, even you could spin it out early, but spin it out one at a time per application, rather than fundamental chemistry and let problems come to you.
I think the applications do come one at a time, but they might come in short enough intervals between them where they look like a shotgun. But I think your point in terms of keeping, you know, what is best, and at some level, I mean, it's nice to keep focus, and, you know, heck, then you can maybe start 4 companies rather than 1, right? I mean, that sounds like fun.
Department head.
I know. I have limited time these days.
More questions? I have to ask you, there's no such thing as free volume because you have to pay for it.
Okay.
And a lot of your examples do entail filling that free volume, and except for the low K.
Okay.
And I'm worried about, you know, how stable are these things, and do they really work? And
If
can you
they're
spin them on?
completely non-compliant structures, they seem to be extremely stable. They don't, you know, we haven't got all the coefficient of thermal expansion data on some of these, which is key for the, yeah, but that's good. We have to talk about free volume in terms of research. Alice controls all the space on campus, too, so. so this is why she's sensitive about free volume. So we're always saying, hey, that space isn't being used. Can I have that?
It's not free. I'd like to call all the speakers up here, and if there are any more questions for Tim, we could thank him again. And so I'd like to moderate a discussion. I think we have 3 very exciting researchers from MIT talking about their stuff, and I was struck by the nice grouping we have. We have the bio and microscale structures to understand liver function. We have the metal semiconductor dielectric interfaces on nanoscales to produce electronics, and then we have the chemistry to make novel structures. And I thought I might start by asking these guys to brainstorm a little bit. I mean, clearly, Tim's other life of detector sensor work, and I think he actually has worked with Yole a bit, or can use his fibers perhaps. You know, can't you guys automate Sangeeta's liver chip and detect the function and get it all working electronically from a distance?
So you want the audience here to hear a proposal generating session?
Well, I don't know. I mean, if it gets really hot, you can take it offline. But
Well, the truth of the matter is, Tim's company, Nomadics, we are collaborating with them through the Institute for Soldier Nanotechnology to create a fiber TNT detector that could operate at a standoff distance. So you could actually insert the fiber into locations that the current system is challenged in doing. So that's actually one of the connections.
Yeah, but I'm actually not doing anything. Well, it was,
You're inspiring. Oh, that's right.
yeah, so the technology that Yoel's referring to is with Vladimir Bulovich, we showed that you could use attenuated lasing in organic semiconductor polymers. And by using a lasing signal, you could get yet greater enhancements. We already have a very high sensitivity, but you can get even greater enhancements in the sensitivity. But we weren't doing it with anything near this type of sophistication of a photonic structure that is Yoel's bread and butter. And so he proposed ways to actually kick this in up to where it would be moved from a laboratory demonstration, which got us a nice paper in Nature, but to something that really functioned and could be fieldable. And so that was a key. That's where that work is headed.
So Tim, Sangeeta's cells kick out things like albumin and urea and stuff. I mean, you got all that, the structural stuff to start interfacing with other molecules, biomolecules that might alter your free volume.
Yeah, I mean, I think looking at metabolites, if that's something, and particularly in a microfluidic platform, and I don't know how much of that you're doing, but with Klaus Jensen's group, certainly he's somebody, making essentially molecular components that can go into these devices is something. But one thing I have to make sure is I'm not a device guy. I just make the materials.
Well, I wanted to just actually add, so we do a lot of biomems work, we do a lot of micro devices, so an interface that you might not be aware of is we made these surfaces, we call them smart Petri dishes, with Michael Saylor, who was on sabbatical in your department. So these are photonic crystals, they're one-dimensional photonic crystals, so they're multi-layer porous silicon Bragg stacks. And we modify the surface so that basically it would alter the reflectivity when something that the cells made attached to the surface. So these are sort of much fancier detectors, and I didn't put them in my talk because they're, I guess, high risk. But yeah, we're very interested in ways to do online detection.
I guess you get the impression that MIT folks collaborate a lot with one another, and one of the pleasures is to come together and learn about some of your colleagues' work. But I would like to open it up to the floor, ask any of us a question, maybe specifically or generally. Doug?
Can you describe how your business life and your academic life work? Because, we hear throughout the year this discussion of founders presenting companies here, but they don't necessarily have the whole academic side to the life. And so at what point do you find that you need to bring other people in to help run the business who are not on your student teams or otherwise doing the research ethic of the school?
Yeah, Tim.
Well, first of all, the first thing that goes, this has happened, the undergrads say this, is first thing to go is sleep. So you can't sleep much. But I do think that having people drive the business and having, that's something that is very important, in having people that mainly to help get together and to get the financing. I think that that's something that I find that when you're teaching, for example, or if you're a department head like I am now, but what happens is all at once that's your job. That's the job you cannot drop the ball on. You'll drop the ball on other things, and you'll have to punt on your entrepreneurial activities, because you have to go in front of 300 kids and give a lecture, and there's a pride, and this is your day job. This is what you're here to do. So you're often conflicted, but you that's what can happen when you try and get academics. It can't be as responsive as you always would like. But having somebody involved in that from the business side is very critical. Is that the right answer?
Yeah. Well, we do have getting the right team. Getting the right team together is extremely critical. We do have the venture mentoring service, which does help. I don't know if you guys have talked to them, but volunteer mentors who will advise faculty and students and other, young entrepreneurs or entrepreneurs working out kind of that bridge between the great technology and the business. Nita?
I think the answer is really that the ideas for companies come together and they percolate with professors for a long time. But the companies don't come together until there's a full-time somebody else to drive the bus. That is, they don't come together with a professor and a graduate student and continue on that way. You have to have outside management. The scarcest resource for us at MIT, helping to catalyze new companies off the ground, are experienced entrepreneurs who are willing to take on such early stage companies and start to drive the bus. We can find money. We find it harder to find the entrepreneurs.
More questions? And Tim, in your experience, have you dealt with, you must have dealt with this whole transition of management and finding the right people.
Well, yeah, I think for example, I think every faculty has, how many virtual companies are in your brain right now? I mean, I think, I can't imagine Noel he's double digits, I'm sure.
Yeah.
But virtual company concepts is something you're always thinking about and you're having in the back of your mind. This is my own personal experience. I mean, it's trying to get out of the gates and get somebody. A lot of times the people that are interested in starting a company, they have a day job and they need a salary. And so an entrepreneur, I always define entrepreneur as somebody that can launch in and just go in and jump into it, and they don't have to worry where their paycheck's coming from. And so I think that in my own experience, that trying to find people of that nature that can drive it and have track record. Usually when they don't need a salary, they have a track record. That usually comes with it. They're successful. And so that's, I mean, I know my own experience, Lita was right on the mark. That's what I need. And
where does the responsibility fall?
Is it that the research team or the professor has to run with it and then start looking for these other people, or is TLO helping out? Is it just people in the audience here?
I described it as coalescing, a fog that coalesces. When you talk to a lot of people, you can use student business plan teams to start making the potential business more coherent, to an initial line definition of strategy and markets. Fortunately, under grant funding, the science keeps progressing, so even after we wait 6 months, well, then it's a little further along. That's the good and the bad part. Professors have real jobs, so they don't have to get moving on this stuff, and that's both good and bad. And eventually, somebody finds somebody. I mean, it's like being past college age and finding a spouse. You just keep running into people, and eventually
You had a Sloan person
Yeah, I
in
was
your.
actually just gonna.
Yeah.
Absolutely. One of the fantastic things here is really the diverse set of skills that exists on campus. I think the Sloan School it plays a very, very important role. In the case of OmniGuide, really, it was actually a Sloan student at the time, Uri Kolodny, who had this vision and passion for going out and starting a company and identified the set of ideas that I was working on at the time as a graduate student as something that he just really attached to. And I actually was very reluctant because Alice could tell you it's a very risky proposition, and Lita she always says that it's fine to start a company, just get tenured first. So doing it So doing that right when you start is very risky, but ultimately, I think you feel that it's a privilege and it's an obligation. And the privilege is just being able to, make things that really have an impact on people's lives. And the obligation is that we're all sitting here, through taxpayer dollars, through society that really is endowing us with enormous resources. And so you get, your promotion is off by years. So what? I mean, you've really, I think, paid a debt to society, which is ultimately a lot more significant than anything personal gain you have from it. So that's.
So I was sort of intrigued by this description of people, wandering around after college looking for spouses, because some people don't find spouses, and I'm wondering how many of these incredible ideas in academia, which could go on to be very useful products for humanity. I wonder how many of them actually just stay in academia and never become realized for the benefits of other people. I mean, if Yoel has double-digit ideas for businesses in his head, and it's kind of hard to start double-digit numbers of companies at any given point in time, what happens to all of those ideas?
So the question is, how many of these great ideas stay in academia and don't ever make it with the right match or the finding the business person?
So I'd like to say that it's an excellent question, and it really doesn't have an answer. What I can say is that I think there's quite a few. And there's a lot the university could do by virtue of its policies and the way it conducts itself that could actually ensure that many of those basic solutions to problems that society have would actually get out. I think having a few people here from the administration, I think it would be actually very good to rethink the basic strategy and to really consider what we're losing by not having these key ideas come out. And I feel that the university in many cases takes a risk reduction approach. And I think it's a very natural approach to take. But the alternative, which is that of not doing things because you're risk averse, I think is not a good one. So a new balance needs to be struck.
I guess I'll just add to that and say that I think many more of these ideas get out at a place like MIT than a lot of places. The 50K competition, the mentorship program, the TLO's activities are quite successful, and a lot of places are envious of our track record, our location in Cambridge, and our community. The policies I think Yoel is referring to are actually federal policies. We take in a lot of federal tax dollars, as Yoel indicated, and we're obliged to minimize, remove, minimize, or manage conflicts of interest. And if there are federal funds involved in research, and the research is connected to a product that will result in financial gain for the inventor, which is one of the great features of our university system, the U.S. patent system, we have to mitigate that financial conflict of interest because of the view that you're handing federal money to researchers and they're getting personally wealthy. Then there's institutional conflict of interest, that you're funding research and the institution could have conflicts. These are very tough challenges. Every place deals with them. There's particular concern when it involves medical and especially clinical trial work, which we do not do here. So that's a bit easier. But we do our best to manage conflicts in a way that will seem reasonable and fair to the outside world. That may look conservative on one side. It may also look, to somebody's mother reading about in the Globe, it might look differently. And so we are trying our best to be faithful stewards of our federal research funding and deal with these issues in that way. That really killed the conversation. I was talking about, is this on tape?
I will attest, so I've only been here 6 months, and this, I hope soon will be company idea. I'd had for, 6 years at UC San Diego, and I've got funded and being here 6 months. So, I think there is something special about the environment at MIT.
Yeah, the Deshpande, I should say that also the Deshpande Center has been a great program for allowing people to take their research from that great scientific breakthrough to a little bit further along towards the application.
First-hand knowledge that I have been passed on to me by a reliable source, but apparently there's a competitor 3,000 miles to our west who has just a higher success rate of bringing concept to fruition. And, talk to Yoel about, thinking about things, maybe that model already exists, and what are they doing better?
I will tell you that we've done a side-by-side comparison with Stanford. We're very good friends with them.
When I say Stanford,
I used to work
numbers are almost identical.
are they really?
Yeah, I used to.
That's why I said it was
Lots of
hearsay.
legends, but they're almost identical. In fact, I pulled that comparison numbers together at the request of Dr. Gass.
We should both be working together to figure out how we can enhance that.
We do work together. I think the research universities in this area work together to understand and how to best deal with these issues. But I do have one disclosure to my name and a patent, and I did it at Stanford, and I can't say that they're better than MIT. So.
Well, but I don't see it competitive. I mean, to tell you, for example, Kathy Koo is my equivalent at Stanford, and she and I meet together at least once a year to benchmark against each other. We used to also have our equivalent at Harvard, and the three of us were the Big Girls Club. But Kathy will be in town in 2 weeks, and we will do it again. So we do indeed compare and learn from each other.
Could you tell us, please, who the lady in red is?
Oh, that's the lady in red is Lita Nelson, our director of our technology licensing office.
Lady in red.
Do you want to say anything?
Yeah, I wanted to say that I think the issues that were raised are very real ones, and I don't think there are any simple solutions. It seems like one of the percolating issues is that of conflict of interest, and tying financial gains with research. In my view, actually what drives researchers is not the financial gain, but in fact the ability to impact society, to bring out your ideas into the real world and to make a difference. And in that sense, it sounds to me like there are some opportunities to decouple and actually be able to bring out the ideas into the real world. And financial gain, I think, can be, and I think is viewed by many researchers as a secondary or significantly lower priority issue. I'm still riding my bike, so no financial gain to date. But having said that, so I think creative thinking, not only in part of the technologies, but actually in terms of policy making, could have an enormous impact. That's my.
It's after 8 o'clock. I think you have another festivity. Oh, there's one more question.
VCs around Boston have entrepreneurial residence in launching new technologies.
Do VCs around Boston have entrepreneurial residents?
Entrepreneurs and residents.
Oh, I see.
Yes.
And how much do you get with that?
We know them very well. When they're interested, we match them.
They're around. Lita knows everyone. So now you all know Lita. Thank you very much, and let's thank our speakers once again.
We will.